Squirrel cage induction motor, speed, torque, and current relationships. Now, analyzing AC SCIM motor characteristics is most often accomplished with the use of graphs. And so we're going to use that when we're looking at the torque, the current, and the speed of the motor, and what happens when it's started, when it's loaded, and when it's not loaded. What about when it's overloaded? We're going to look at all of these different situations. The first graph that we're going to look at is a fairly involved graph. And the reason it's involved is because we have all the possible worst case situations placed into one red curve. Now we're going to break this down a little bit and discuss each portion of it in a separate graph further on within this presentation. But at this point, what I want to draw your attention to is the way that the graph is set up. We have a vertical axis here, which is the value of torque, increases as it gets higher. Over here, we have the horizontal, which is the speed of the motor. And when I say motor, I mean the rotor or shaft of the motor. All the way up here, we have synchronous speed listed at 1800 RPM. Over here, we have the nameplate RPM at 1740 for this particular motor. And then all the way back here, we have a number of 1400. And there's another dotted line. It says breakdown torque. So we're going to discuss that in a few more slides and see what exactly it's referring to. Now, the way that the graph starts is obviously from the junction here, and we're saying at 0 RPM, the motor is started with full voltage and a full load. And this is the amount of torque that the motor will be able to generate in order to start turning. Now, what happens after that, we're going to start discussing. And really, this is so confusing because on these types of graphs, what the manufacturers have attempted to do is provide sort of a laboratory curve to show all the possible situations in one curve. And it can get a little confusing. So let's look at the motor torque graph for a unloaded motor, a fully loaded motor, and then we're going to extrapolate and discuss further what breakdown torque really is. So this is the torque graph for a SCIM motor that started and run with no load on the shaft of the motor. And so because of that, because there is no load, it means there's no counter torque that the motor is trying to match. All it really has to do in this situation is overcome the stationary inertia of the rotor itself, nothing more. And once it gets up to speed, it almost needs no torque at all. And so we can see here that the speed of the motor is actually a little bit higher than the nameplate. Remember, the nameplate speed for this motor was a little bit slower than 1798. It was 1740. So if I run a motor with no mechanical load, I would expect it to run a little bit quicker. This is a graph that shows a SCIM motor that started and run with a full mechanical load connected to it. Again, what we have is a full voltage start at 0 RPM, and there's a significant amount of counter torque that's being applied to the motor shaft. What this means is that the motor has to develop a significant amount of torque in order to overcome that, again, stationary inertia, which in this situation is quite high. But as it starts to turn, the inertia, the speed of that rotor, requires then a little bit less torque from the motor until eventually, right at this point, we reach what's called the full load speed, which is the nameplate speed, and the full load torque. Now, the full load torque we can calculate with the horsepower and the speed of the motor. But why does it drop off so suddenly here? And what is that all about? So let's look at this portion of the curve, because this is really where most of our daily activity working with motors will be found. So let's blow it up a little bit and make it a little bigger so we can start looking at what occurs in different situations. So first I want you to draw your attention down here, the synchronous speed. Now, the torque drops down to zero if the rotor was ever able to reach synchronous speed. Zero slip would occur at that point, which would mean zero voltage would be induced into the rotor bars, which would result in zero current in the rotor circuit, and finally, zero torque generated. Whew. So the motor is currently at this point running at nameplate RPM, and that's because it's delivering its full load torque and it's operating at this point here. If we were to operate the motor under load, which is far more common, what we find is that when we apply a load that is less than the nameplate rating of the motor, obviously the torque that the motor must supply to turn the shaft is reduced. We can see it's lower down here, but also you see a correlation with the speed. So as I start to reduce the amount of load that the motor is driving, I actually increase the speed of the motor shaft. And that's because we are providing less mechanical opposition to the motor shaft turning. Now, what happens when the motor is overloaded? So when we have a mechanical load that exceeds the rating of the motor, we're going to have a motor that's now delivering a little bit more than what it's rated for. And so we call this an overload situation. Now, when a motor turns a mechanical load that exceeds its nameplate rating, we say it's overloaded. And during this time, it will increase the torque in order to match what the load is requiring. Notice also that down here, the speed of the rotor decreases. So as I continue to overload the motor, the speed of that rotor will decrease, decrease, and decrease. Eventually, I will reach a point if I continue to increase the mechanical load, I'll reach a point where the motor is no longer capable of developing the necessary torque to continue turning. And so I've chosen arbitrarily to choose the number here, 40% overload. I'm not saying every motor is at 40%, nor am I saying this is a number to memorize. This is purely for example purposes only. Now, the maximum torque that we are going to see is when the torque curve flattens. And we refer to this point as the maximum breakdown torque. The motor is incapable of developing any more torque at this point. And if we were to increase the mechanical load even by a gram, the motor would then result in going into a stall condition. So a motor that has a mechanical load applied to it that exceeds its breakdown value will be incapable of turning. This is called stalling. And in an electric motor, stalling means the rotor will quickly come to a stop and high stator current will result. Now, if we don't immediately de-energize the motor, it's likely going to suffer damage due to the really high current that is going to be flowing through the stator. So again, to bring us back to this full graph, what we see is the entire situation of realms of possibility that the motor could experience. This is the maximum starting torque that we could perhaps have with the full load attached. This is the maximum breakdown torque that we cannot exceed under any circumstances, otherwise the motor will stall. Finally, under normal conditions with a full load, the full load torque is being developed by the motor. And if I were to decrease the amount of load that the motor is driving, the speed will get higher. Now, it's interesting to note that although breakdown torque is different for every motor, it always occurs when the rotor electrical circuit achieves a power factor of 0.707 or 45 degrees. And what I mean by that is if we were to extrapolate and look at all of the characteristics of the rotor bars themselves inside the squirrel cage, we would see a similar type of graph that shows the current, the resistance, the XL, and all of these different factors happening at the same time. Now, the rotor is actually its own isolated electrical circuit inside the motor. And as the rotor speed changes, the frequency applied to the rotor bar changes also. This leads to changes in the XL of the rotor as the rotor is increasing in speed. Well, this then has an effect on the magnitude of current flowing in the rotor bar. And since the torque developed is directly proportional to the amount of in phase current, it means that the maximum torque or breakdown torque will always occur when the power factor of the rotor is at 0.707, which is where the XL or out of phase current is at its lowest value when compared to the IR or in phase current. Now, we don't have to go into great depth on a graph like this. Instead, all we need to bring to the table is to understand that if the power factor of the rotor circuit is 0.707, that will be where the maximum breakdown torque is achieved. Now, how can that be changed? Well, the physical design of the SCIM rotor determines the motor's torque curve. And depending on how I construct it, I can get different values of resistance or inductance. And as the motor is run, that will lead to different curves. So here's an example of NEMA design A. Not really of much significance until we compare it against another design type. This is the oldest type of AC motor design, and you can see here that the rotor or scroll cage bars are actually going to be quite long. Here's a NEMA design B. A little bit different, but man, that is definitely the most common rotor design we see with SCIM motors. There's a definite difference between how they have arranged the depth of the rotor bars and also their width. NEMA Design C is really quite different, and it's often referred to as a dual cage rotor design because it almost looks as though there's a cage here and a cage up here with the rotor bars. Uh, very specific design shape for the bars. And finally, here's NEMA Design D. Now, each of these has a characteristic that might be desirable in the field when we're attempting to select a motor. And we're going to look at that in a little bit more depth. Now, once a SCIM motor is manufactured, its torque curve cannot be changed unless specialty motor starters are used. And so what this leads to is very different torque curves for different rotor designs. A and B are by far the most common, B being the most common, hands down. And that's sort of what we've been looking at with our general torque curves up to this point in the presentation. C, that's a different type of motor. And that rotor in there has a different resistance value, which means that its starting torque is a little bit different as well as its breakdown torque. So a NEMA C designed rotor has a higher starting torque than a NEMA design B or A. And finally, way up there at the top, this is a NEMA design D rotor. And you can see that the starting torque is significantly higher than any of the other NEMA rotor designs. So an engineer will look at this information and say, well, I'm going to select a NEMA design D motor for this application, or B or C. Not really A, it's not really used that much anymore. Here's a really quick graph to show some of the uh, basic types of applications and their breakdown torque in relation to one another. It's good to have a general idea as to the starting torque, the starting current, and the breakdown torque. Motor torque and RPM and stator current. Now, this portion won't be nearly as in depth or long. We want to simply look at what can we expect in the field when we're working with motors. So here's a full SCIM motor torque and current graph. And in the same way that we looked at the torque graph, we said really it's showing all of these different situations at the same time. Now we can see that the rated speed is right here, and that's when it's driving its rated load. So the rated load would be the rated torque. But in this graph, what we have is the current shown on the vertical axis. So we will have it the rated nameplate current when we are driving the rated nameplate torque, and it will also then exhibit the rated nameplate speed of the motor. Now, the motor starting current can be several hundred times higher than the FLA, and this happens when the motor is started with a full and stationary mechanical load. Now, typically this is okay because the amount of time the current is present is actually very short. I've listed 2 to 15 seconds here, but of course, there is quite a large range depending on the type of motor we're discussing. If the inrush current goes beyond a minute, it's likely we're going to have damage. So let's take a look at a graph that shows the starting current and running current of a SCIM motor if I have no load connected to it. Well, if we have no load connected to the motor, the torque value should be incredibly small. And due to the very low amount of torque generated or needed, the current will also be low. So the motor current would be well below nameplate FLA, and the motor speed would be above nameplate RPM. If we were to start the motor with a full mechanical load, as we did in the previous examples, then we would expect a fairly high value of inrush current, and you'll notice that it starts to drop off very quickly once we get close to the rated speed that the motor should be operating at. So the current that is actually drawn when we start the motor can be calculated with the NEMA kVA code on the nameplate. Now, when the motor is running, which would be right over here, the current that we measure on the stator conductors should be equivalent to the nameplate FLA, and the speed that we measure with a tachometer should be equivalent to the nameplate RPM.